All right, so let's get started. Today's speaker is Yao Xie. She's from Georgia Tech. She's a search professor at Georgia, and also it's a long name, Harold and Mary Ann Nash Early Career Professor at the School of Industrial and Systems Engineering at Georgia Tech. Yao graduated from Stanford with a PhD at Stanford. Two advisors joined, and including one of them is David Sigmund in statistics. This is what, she was in ECE PhD student, but she told me she worked more with David Sigmund, who is in statistics. And this long list of accomplishments. I mean, her research interest is amazingly broad, right? So typically statistics, but also on the sequential decision making. What really amazed me that that's really her diverse application areas, diverse areas, not necessarily application areas, but including applications. And among her honors, Agnes Career Award, and later on at this Informs meeting, she's in the finalist of Wagner Prize. That's something. Congratulations. Okay, so that's it's a great honor to be in that league. So I think today's work may be something will tell us a bit more, somewhat related to the Wagner Prize. Okay. Go ahead.
All right. Great. Thank you so much, Jim, for the very kind introduction, and thanks everyone for coming, and thanks for the invitation and a great opportunity to be able to visit the department that I've heard so much about already and know many friends here. So I guess I have about an hour, and so in this 1 hour time, I would like to talk a little bit about a topic that I've been working on in the past couple of years, which is modeling discrete events data over networks. And so it's basically, on the high level, how to estimate a network using streaming discrete events data. I'm going to describe this from the perspective of continuous time and discrete time setup. Okay, so what is discrete events data over networks? And so here's an example from social networks. And this is where I started to be interested in this, working with my colleague Lisa in computer science at Georgia Tech then. So in Twitter, for example, you have this large network with many users, and you can observe sequence of events. For example, user A retweeted the picture at some time, user B liked the picture, user C commented at another time. So by looking at these events, which tell us what user did what at what particular time, and the sequence of events, we can sort of infer, are they friends, are they close friends, are they sharing some common interest? So can we figure out this underlying connections between the nodes in a network is of interest. And so this makes me start to be very curious and interested and find out this actually has many applications from different setups. So social networks just talk about, and in the neural network study for brain map, it also occurs where you can see the data is so-called neurospike trains at different locations in neural networks, and seismic activities where you can observe earthquakes which happen at some time, location with certain magnitudes, and criminal activities which are these bad incidents of breaking into the houses at different locations. And then disease transmissions, the events are the confirmed cases, the deaths, and different activities, events happen at different times and locations, and power grids and stock market, and so on. So it's actually, a lot of these applications are interesting to figure out this underlying network using the observations which tell us the time, location, and information, or so-called marks. So the discrete events data is in the form of the time, location, and the marks. For example, in social networking, Twitter or Facebook or LinkedIn, you have this information about who did what and some description and the time. And the neurospike train, the data looks like for this particular location, you have a sequence of these activities. And in earthquake catalog, the form is at what time, location, the magnitude of earthquake. There are actually many, many earthquakes. It's not just major ones, but the small ones. And this is very important for seismologists to understand what's happening and build a model. So for crime data, the most commonly seen events data are the police reports. Whenever you call 911 and the police officer will respond to the call and arrive at the scene and create this report, which is usually an electronic record. So put down the time, location, and categories and many information, also a narrative part, which is their description, free text, what actually happens there that contains a lot of information. That's treated as a mark. And the COVID-19, for example, you can have the cases and the deaths and so on, and whether or not there is intervention or closure at different locations in the US. So another example is power outage data, where you can observe where, when, and the power outage, how many users are experiencing that. So these are informations. And so this actually application came from a collaboration with Argonne National Lab. They're one of the leading national labs studying outage data and predictions. And for financial data, the events data are, for example, in limiting order book, when the order arrived, when it's being executed, and so on. And so, so what are, something we're trying to find from this data is the triggering or inhibition effects of events over space and time. So what does it mean? So if you want to make a prediction for understanding the dynamic or the impact of the events, usually we assume, the past event will have an influence to the future. And for example, if there's an earthquake happen somewhere as time goes by, and there's another earthquake happen at another location with a different magnitude. So one is a potential trigger of the later on earthquake. And so if there is a model based on many observations of the earthquake, we can understand how the past event will trigger future events. That will be a very useful model for making prediction, understanding the dynamics, and so on. So this actually is so-called the ubiquitous model in seismology that uses this earthquake-like discrete events data to build models to making predictions. So we had a collaboration actually with one of the colleagues in earth science at Georgia Tech, and we had a paper. And so you can see using data for studying seismology data is of interest for the machine learning community as well. In Europe, they have this kind of conference. And so interestingly enough, I find a similar kind of influence, modeling the influence occurs in crime data. So the past events cause future events. In criminology, there's a famous effect called the broken window effect. So once a neighborhood has a crime incident, similar crime is more likely to happen in that particular area. And this problem came into our attention because in 2016, a group of police officers in the Atlanta Police Department reached out to us and saying we were interested in collaboration. So it's really interesting that they show up at our department saying, like, with guns and badges, and saying we want to work on data, not causing any trouble, but they want to work on data. And so they said they have millions of cases in their database, but these police records with lots of free text that hasn't been processed. They have a police investigation unit with maybe 20 experts, but looking through all the reports, the free text is very laborious, and finding correlations between incidents is, without any automation, these cases become cold cases. It's not easy to find the linkages, so-called the crime linkage. So they said, can we develop some algorithms to help them to find hidden connections between the crime cases? An example is given by them saying, in 2017, there were 22 cases committed by a serial offender. If you look at these cases, they're all, centered around this Buckhead area, which is a rich neighborhood in Atlanta. Actually, by looking at these locations, I realized it's highly related to my life because my home is somewhere in the middle here. So for the first time, I feel like my research is highly relevant to my own life. So if the purpose is we're able to monitor and catch the highly related cases, then hopefully can catch the bad guy before he even done 22 breaking into the houses. And so this later on released to a paper recently accepted by Analyst of Applied Statistics and in collaboration with the police. This is the beginning point of that. And so as you probably already noticed, so in the different form of applications, there are two kinds of locations. One is the traditional spatial location. You actually talk about locations. And usually the underlying space is clean. You talk about things, two locations are close to each other, then there is a strong correlation. But there are some problems, like in social networks, the underlying space is a graph. So in this work, and also in many current work, we tend to consider both type of connection through a network. So the motivation is, for example, you look at COVID-19 spread, and so you can have two things going on. One is that there are some cases here, and then the nearby locations will tend to have higher cases in the future. So you have the spatial affinity will indeed induce more correlation. But there are also, for example, Las Vegas is closer to New York City because they have direct flight. They're both airport transportation hubs, but they don't necessarily close to each other in space. So this can be captured through a graph distance, right? So if you can create a graph and saying they're just one hop away. And so by combining both type, and so that means we can, for example, discretize the space, and then you can induce a graph where this one has an edge between this with the neighborhood, but also there are some additional edges between these places. We believe they have the hops then that can be used to model the dynamics. So we use this in two of papers. Okay, so in summary, what we're trying to study is given this sequence of discrete events data, which is in the form of the time, location, and the mark. In general, captures the category, description, and so on. So this mark can be high dimensional. Can we possibly find out a underlying graph, the connections in terms of the graph? And in particular, if something happens at one location, one node, how does influence the future for other nodes over time? So it's going to be over time, and also it's going to spread over this network structure. And for example, if I have a graph like this, and node 1 to 3 have a sequence event like this, and so these different types of errors indicating different kind of information, different kind of events, and you can have a interdependence between the events one causes, and this can cause future events on itself, but also triggers the events in the nearby nodes and so on. So how do we find out this hidden network or influence? So this is going to be different from the traditional IID and time series model because these events can be asynchronous. The actual timing information is important. So coming from statistical background, the most commonly made assumption is IID, but IID, you can capture the interdependence between the dimensions, but ignore correlation over time. And time series model can capture, discrete time series model can capture dependence between instances at different times, but again, you're sort of assuming these events, you can represent time by a discrete index. You assume that they're somehow happening in the same bin, so the detailed time information may be ignored. So how do we model this discrete events data? And being able to recover the underlying influence network and influence over time. And like I said, this can be useful for many things. Okay, so the answer, or one of the popular approaches actually lies in a pretty old model, the so-called Hux Process Model. I'm sure many of you are familiar with this. It's a type of point process that captures the influence of the past. That captures the fact that the past events will have an influence to the future. And so this is Alan Hux. He's a professor at Durham University in UK, and he published a paper in the 70s. So basically about this Hux process. So in general, quickly, suppose we consider a one-dimensional sequence of random events, and then we can capture the distribution of this using a conditional intensity function. This is like the basic stochastic process. And in particular, you could say that given the history, then the chance of having an event in a small interval is going to be described by this conditional intensity function. Okay, so either way, and this is a natural framework for prediction because this is saying that I incorporate the past information. If I can have a certain form of my conditional distribution, I can predict the chance of having something in any given time. And this can be generalized to location as well. And so some common form and Poisson process is to say that the conditional intensity function is deterministic. And Hux further says that it's deterministic, but also have a component that captures influence from the past. For example, if the influence from the past is positive, so you can, whenever you have an event, maybe this increases the chance for the near future, but this influence will decay over time gradually, so you wash out the influence gradually. And the influence can be positive or also negative, and you can have the mix of the two. Okay, so the key question here is you need certain form of parameterized as conditional intensity function, and so the most commonly choice is this lambda t will be the form of the baseline intensity function plus this term that captures the influence from the past. And so here, alpha is a parameter controls the magnitude of the influence, and this is the superposition of all influence of the events from the past. And this particular choice is the kernel function that captures the influence of the case event happens before time t on the current. If I choose the phi to be a particular form, for example, we can measure decay, it looks like this. So I can see that the total influence is the sum of all of them, but they also gradually wash out. So this particular choice is going to be helpful because then each event essentially causes the same kind of influence. So we can estimate the influence if you have many observations from the events, and seeing repeatedly you have the similar kind of influence, and you can estimate the influence function. And so what about the Hux network? So this generalization becomes, it's a special kind of multidimensional Hux process, but it becomes very popular in statistical machine learning. So if I have a network, then I have a process at each of the nodes. And I capture that by a conditional intensity function indexed by I. I is the node index, and so it's the baseline plus this part. So now the alpha is going to play an important role because that tells me how events happen at one node influence the events happen at another node. So I can have alpha ij captures how node j influence node I. And so if alpha ij is 0, that means the two nodes has no influence to each other, for example. And alpha ij can be directional. So that means this can have influence on 2, but 2 doesn't have influence on 1. And I can also have self-edge, means the nodes will influence itself in the future. And so if we can figure out this alpha ij, okay, which can be viewed as a directed graph, then we can know who is influencing who, and basically this captures the nodal influence. But this together with the phi is how the influence propagated over time. Then these two things essentially is a decoupled kernel of the influence. And so if we can learn alpha and the phi somehow, then we can be able to use this to understand our data and propagate into the future. Yes? Question, please.
So how does the model, like the Hux type model, implicitly disentangle the seasonality / time varying question from the self-exciting question in some sense? Or is it high tomorrow because it was high today, or because just the time parameter tomorrow dictates that it will be high?
Yeah, that's a great question. So basically, I think that is captured through here. So there are two things, there are two effects happening. Like this one is the intrinsic variability, like you said. And if I average, for example, I know summer is a high crime season. It's just always the case. That's not because yesterday there's some bad events. But the excitation part is captured through here. That depends on the data. So the data is the TK and the UK. So TK is when the case event time, this is the case event location. So if I can disentangle this mu and this part, then I can separate the two effects. Did this sort of answer the question? Yeah. Yes, Christina, please.
The mu is assumed to be known?
They have to be jointly estimated.
Both need to be estimated.
Both
right?
needs to be estimated.
Also
Yeah.
Yes.
Oh,
So this needs to be estimated, and this, fine. So you basically, if we can do that, you have a completed, decomposition of what goes to where.
So
Mm-hmm.
should I think about this network, the very large network?
This network?
Yeah.
So this can be ranged from small to large. So the how to scale this up, how to scale the estimation to large graph is some of the focus we want to address here as well. Great. Yes?
Yeah, just when you're estimating it, you're assuming some kind of form of phi, for example, Markovian or something else.
Oh, yes, that's a great question. So what about the phi? Okay, that is a very important question. So like I said, given the data, in order to estimate, we need to estimate the mu and the alpha and the phi together. But jointly estimate alpha and the phi can create some problem because you can have essentially the multiplication of the two factors.
Mm-hmm.
And so that's going to cause non-convexity issue. I'm going to talk about how to address that as well. Yes?
What would change if you say alpha can be 0 or 1, and then the phi has to be, different for each segment, right?
Oh, yeah, that would be interesting. So to what extent can I generalize the phi? Here, this phi, essentially that means for all the events, they have the same influence pattern. But you can have different kinds of events, right? And that has different phi's. And so this can be modified and extended to that particular case, right? So I have a particular form of the influence, but I can make this depend on U, for example, or some other parameter like indicate the type of events. Yeah, and then you just have more phi's that you need to be estimated. For example, like COVID-19, you can have the death event and the confirmed cases. They have different impact on the future. Yeah. Great question. I think this is actually a very important slide, so that we need to dig into. And exactly like has been noticed by Katia, that the choice of the phi is important. And so the most common choice is the exponential decay, and it's controlled by the parameter beta. That's like a time constant. If beta is large, then I have longer memory, otherwise I have short memory. And for this particular choice, it's common because the induced Hux process is Markovian. But it has been shown that a lot of times this is not enough. So we want to go beyond the exponential setup. Okay. Any other questions? Great. Okay, so it's not a new model, but somehow why this became popular. Okay, this is my conjecture based on working on this for a few years. I think why it became so popular, you can even look at the machine learning conference, Google search Hux process, you can see so many papers, search point process, everybody seems to be excited about it. In applied math, in statistics, in machine learning, everybody's talking about Hux. I think part of the reason is, now we have a lot of data and computational power. And we also need, this is a very general framework of capturing the model for discrete event theta and use this to make a prediction. And so I find this interesting quote this is a PhD thesis by this author, and it said, in the past days there was a hope that Hux process will be the new AR process for this discrete event data, but it didn't happen in old days because you don't have this large amount of discrete events data, and there's all kinds of computational challenges that is not addressed with limited computational power. You don't know how to solve large-scale optimization problem and so on. So now this is different. And exponential kernel have certain limitations. And now we want to go beyond the exponential kernel as well. Okay, and also need to address the high-dimensional mark. So this is all arising from the new type of data that creates a challenge we want to be able to solve. Okay, so here is a brief, basically incomplete reference of what has been done. And like I said, this is really booming area. I think that's not new, but it becomes popular again. I take some of these from statistics and machine learning. I think there's even more in the OR literature. People use this for studying queuing process as a rival process modeling and so on. So a lot of these has been focusing on estimation parts. Okay, so what do I want to talk about today? So I want to focus on model estimation as we discussed. And in order to estimate the model, we need to estimate the baseline, the mu's, the phi's, in particular kernel, the influence that captures how events influence propagate into the future. And once we have that, we can extract the network structure, use this to make a prediction because it tells us the probability of certain things happens in the future at one location for a certain time. And use this to monitor if there's any change to the underlying dynamic. It's also useful for causal inference because this graph structure actually has to do with Granger causality. And finally, of course, use this for any kind of decision making. So that's the purpose here. And so, what are some decisions to make in terms of estimating the model? And so, we need to have a good representation of the kernel. That's going to critically determine the computational complexity and statistical efficiency. And like we said, so the common choice is to decouple the node interaction with temporal influence, because now you have a nice expression like this. And then if I know the phi, just estimating alpha and the mu, we can show that the problem is convex. But that creates some limitation because what if I don't want to assume this phi, I want to join and estimate this whole thing, then can I still be able to have some computationally efficient algorithm with guarantees? And what about I want my temporal influences non-stationary, but what that means is this only depends on the current time t and the past event time tk. So in that sense, it's basically a convolution of the influence function with a counting measure the counting measure accounts for when the random time occurs. And so what if my kernel, what if the inference from the past is non-stationary to the current? So this could happen because, for example, you have some kind of non-homogeneity. And so can I further learn a more general kernel representation, which is t, comma, tk, okay? Instead of just the shifting variant. So can we achieve all of these? So I'm gonna treat these problems. So depending on how much time we have, but I try to cover some of the high-level ideas for 4 areas covered by some of my papers. So let's start with the first one. So since we're talking about model estimation, and we're going to use maximum likelihood, which is the default choice for model estimation, statistics, and estimation. So for this case, we can write down the likelihood function, which is a joint distribution. If it is considered a one-dimensional case, it can be specified this way. So although the times are interdependent, but I can decouple the joint distribution as a product of a sequence of conditional distributions, right? So it looks like this. And so basically this, you can see, this part is related to the conditional intensity function lambda that I'm going to use to write it down. Okay, so you can see the likelihood function. This is basically the survival function that can be defined. And so using this form, I can end up having the likelihood function for this one-dimensional case look like this. So basically this is the conditional intensity function evaluated at the random event times. That's where the data comes in. And the second part involves the integral of my conditional intensity function over my time horizon. And keep in mind, in order to perform maximum likelihood, I need to evaluate this L. So for example, this integral, right? I need to be able to perform this integral over time horizon. If I don't choose a good form of the lambda, this integral can be difficult. In the 1D case, it's just one-dimensional integral. I can do it numerically. But if you consider marks together with location, with time, this integral will be a high-dimensional integral. I can't simply evaluate this by numerical integration. So that's going to cause some of the computational challenges. Okay, so to give you an example, if I go back to my network Hux process with exponential inference function, you can see that's where I need to assume the phi to be exponential because my integral will be in a closed form. Then I have a closed form expression for my log likelihood function. And I highlighted that the parameters need to be estimated. So you can see the mu, the baseline, and the u's and the t's are the data. The alpha and the mu's are in this, I make them the orange color because if I fix the beta parameter, and then the problem with respect to all the orange parameter is convex. Oh, that is great. So most people are using that and saying let's solve them by fixing the beta. But the thing is, if I want to optimize with that beta and the mu and alpha, then it's non-convex. And so, like we said, we want to solve the optimization problem, and sometimes it's convex, but only under some simplification. And so another thing is when the inference function is not exponential, that integral part is also not in closed form, so it can cause trouble. Okay, so like we said, if it's just estimating the alphas without need to estimate the phi, the problem can be solved efficiently using convex optimization by any of your favorite solver. By gradient descent, you can converge to something. Okay, so I'm going to treat this estimation problem from a few angles. The first one is, can we provide any uncertainty quantification? So the estimation itself is done by solving this optimization problem. And because the data is stochastic in nature, so it's the resulted estimator, this A hat, as a function of data is going to be random. And so can we capture that randomness in our estimate? Because it's going to be important for us to establish any inference, in a sense, for so-called causal inference. If I want to draw a conclusion whether or not one node has influence to another node, I need to be able to answer the question: do they have influence 0? If the influence is 0, means they have no causal relationship. And so I gave an example. This is actually coming from the neural data, and this is based on a neural synthetic data. So we have a ground truth look like this. And if I just naively apply the MLE estimate, and even if I assume the phi is known, this is the resulted network. and it's very dense compared to the truth, because a lot of the edges are fictitious due to noise. And if I just naively apply a thresholding on these edges, I can't recover back to this. So I want to be able to find some uncertainty quantification in the sense I have a confidence interval for each of the estimate that will help us to eliminate the edges. And just to mention why this is important, one example is neuronal data. Another one is for medical data study. So I have a collaboration with Emory Hospital, and so they have a lot of ICU data, and my collaborator is interested in finding how to predict sepsis using the sequence of events. That when a patient is admitted to the hospital, and you have the measurement, and you have the test results, and ECG, EKG, and so on. So what are some important factors that actually leads to sepsis? So in this case, these nodes in the network are going to be these different medical conditions. I want to be able to recover this network that will help us make decisions. Okay, so I think for this part, I will give the high-level idea how to find the confidence intervals for my estimate. So this alpha hat is the estimate by solving MLE by fixing the phi. That the problem is going to be convex, but I want to be able to quantify the uncertainty, the randomness in my estimate. So by relating this back to statistical theory, that we know the MLE is asymptotically efficient or consistent, so it's converging, the difference of the estimate and the true is converging to 0, and then the convergence rate depends on the inverse of the feature representation. Okay, but the thing is, the asymptotic is not very good. When the t is, this is when t goes to infinity, but when t is not, and then this is not going to converge to it's not going to cover the truth. For example, here, this ground truth is alpha ij is equal to 0, which is here. But when t is not very large, when it's here, this interval is not containing this particular entry. So you're going to draw a wrong conclusion if that's the case. So basically what we present is an algorithm that is not asymptotic, such that it will cover the true parameter with desired probability at any given time. So this blue one is our constructed interval is always going to give the right answer with high probability. And so I guess, so what is the secret sauce here, or what is something enable us to do this, is to find a way to look at this instead of looking at asymptotic MLE property, but draw a connection between this and the continuous time martingale. And I would like to highlight that this is a pretty challenging problem because it's not a time series, it's a continuous point process. And it's also not a Poisson process. It has memory dependence on the past. So it is not easy problem at all. So we find some connection between this and this recently became popular approach, connecting super martingales, and be able to use this to establish the confidence bounds. So let's see, maybe I will skip this and just say that in the end we're able to find a way to capture the confidence regions, and that will tell us the right answer. And to solve this confidence region, it can be done using a polyhedron approximation. So you can solve ILP to find this is this basically gives me a box and tells me that the true parameter is likely to be contained in here. So the difference between this and the previous MLE is MLE gives me a point estimator. But now this is going to give me a set estimator that is going to contain the true parameter with high chance, and then that captures the randomness. Okay, so this is a simulation example. I want to show the benefit of this. So basically, in this example, I have a simple network like this, and so so this is the true parameter, and if I use the original asymptotic confidence interval, is going to give me this this pink box. It's a box because it's just confidence intervals. Yes?
Sorry, I just wanted to ask, because I think the usual theory that I know of would give ellipsoidal confidence regions.
Mm-hmm.
Why is it non-ellipsoidal?
Oh, yeah. So here, okay, I think I skipped one step. So you can, the confidence set itself is going to be solved, it's described by some function. So if you have to solve the the function to find the general form of that confidence set conceptually, but it's becoming very difficult, intractable. So we actually find a polyhedron approximation to the actual set.
What is the nature of the polyhedral description?
Yeah, so it's basically like the idea is here. And so, okay, so here is the description. And so basically by inverting, okay, it goes back to all the theory here. So I have a score function, which is a derivative of the log likelihood function. And I look at the deviation of this at the true parameter, and my MLE is related to the Hessian times the difference of the parameters. And if I invert this Hessian, I should have this. So that's the tool to construct the confidence interval. And so, okay, so the idea is that I will try, so first of all, this S is going to be, if I choose a certain projection of the S, it's going to be a super martingale. And second is, if I can somehow estimate the feature information using sequential data, then I can find this description here, and that will help me to find, this is the difference of the two vector. So this tells me the difference of the vector is going to be this quantity. So if I can find a bound for this quantity, this is going to be vector, so I have to talk about bounding a vector in high-dimensional space. That's where the approximation of the sets come in. Yes?
So typically in the sort of normal theory, this side here would be some kind of sphere, and then I inverse is creating some distortion event to an ellipsoid. So what is it about this problem that takes you away from that kind of geometry?
Okay, so this S is a score function. It's a derivative of the log likelihood. Yeah.
Yeah.
So I think the usual setting is you're going to consider intervals. So I'm not sure if it's ellipsoidal or not, but it's if it's ellipsoidal, I think it's assuming it's Gaussian, right? So if you consider individual coordinates, it's going to be a box. The confidence interval for each of the coordinates is a box. But if you consider a Gaussian approximation, then you have the first moments and the second order moments, and that gives you a ellipsoidal description here. But I think here we want to consider this whole thing using concentration inequality, so that basically essentially aiming to capture beyond the first and second order moments. So it's going to give you a more general set. Did this sort of answer the question, or we can discuss more offline?
Thank you.
Yeah, sure. Yeah, so it's the general set is too complicated, so we approximate it in the end using leave. Yes.
Is the confidence interval like calibrated, or is it like an upper bound?
Yeah, it is calibrated. Such I don't know if that's the meaning of calibration you're talking about. So I want to have a confidence level. So I want my set to satisfy the confidence level. So it contains the true parameter with 1 minus alpha, for example, 95% confidence level. Okay.
Oh yeah, no, it is a fuzzy word. I meant like, is the set that you're giving effectively exactly having the desired probability, or is it like a union bounding?
Yes. It actually is very close to what you want. I'm going to show you one example. It is empirically calibrated. Yeah.
It is funny the word calibrated.
It's a pretty good approximation. Yes.
Cool.
I love the word union bounding.
Yeah, that's another.
Union bound. It's yeah. I know what you're talking about.
Yeah.
It's a non-union bound type.
When people use the word calibrated for that concept, I don't know. Yeah.
Yeah.
So it's not just upper bound. This is actually bound is short.
Exactly. It's a
Right,
sharp
okay,
bound.
yeah,
It's a
okay,
sharp
good.
bound. I'm going to show you this using the real data. So basically, if I want if my target level is 95%, and using this method, I can achieve a 96.8. And versus if you use the asymptotic coverage, it's going to be over-covering 100%. It's covering everything. So it's a pretty sharp bounce.
But I mean, does the theory that you just used to derive it, like if you could let your polyhedral approximation go all the way, would it be, at least as n went to infinity, like exactly the asymptotic coverage?
Oh yes, that's exactly right. That's a great question. So we actually have this result here. So it converges asymptotically to the same width with the asymptotic. So it recovers the rational result. Yeah, great. Any other question? Okay, good. Yeah, so this is a collaboration. So we demonstrate this the usage on the neural network study, and this is recurrent neural network study with my collaborators at Duke. Okay, so that actually flying through the first topic, but I hope to give some flavors of these works. And the second one is how do we handle high-dimensional marks? So getting back to the problem of how do we estimate the influences. And this work is probably a slightly more, I don't know, machine learning-ish. Machine learning is an overused word, but yeah. So see how we handle high-dimensional marks. And we need to handle these free text written by the police. Getting back to the story of I live in the center of the 22 cases of breaking into houses. So how do we catch these bad guys? And so there's one important thing which is called the MO. Okay, so basically the police tell us that besides time and location, the text description contains very important information. So MO is modus operandi. So it basically says that the same serial offender have very similar traces. And this can be found if you look at the police reports description. For example, this 22 cases, if you look at description, and if you just collect the high frequency keywords, you can see there are misses, of course, not meaningful, maybe, and home, drawers, jewelry, house, residence, store, burglary, and silver. So basically what happens, in retrospect, they tell that they call this bad guy, and he said, he has a pattern basically breaking into the houses in the afternoon, and he knows where to find the valuables and jewelries in the bedroom. He will ransack the bedroom. So you can see these keywords actually, these keywords actually appears here, like house, jewelry, door, because they dig a hole in the back door, and the drawer and so on. Yeah, so talking about MOs, and if you look at the serial crime provided by the police, and different crime series have different MOs. And so the second is serial crime. I think it's a pedestrian robbery in Buckhead area. You can see the high frequency keywords are victims, males, gun, hoodie, pockets, robbery. So this is a guy that always robs people with a hood covering. And this is pedestrian robbery committed by suspect A, pizza delivery, blackmail, vehicle suspect, scene gave. So this pictures someone who's always like pretend to be a pizza delivery guy and rob. So different crime series have a different, these definition of the MO. If you look closer to the description, you can find them. Okay, so and then we're saying, okay, great. Then give us all the supervised data and tell us 1,000. Identify crime series, and we're going to build a machine learning algorithm from there. And they're saying, okay. And then they came back and with all the 6 serial crimes, they said, oh, we're pretty busy. Our colleagues don't have the chance to collect a lot of supervised data. They just throw, a bunch of crime reports to us. Like we have 1 million cases in our database, which is not labeled. We don't know whether or not they're related, but this is the amount of supervised data we can give to you. 6 serial crimes with about 54 cases. It's almost become an unsupervised problem with minimum supervision. So how do we build a model to be able to capture the correlations between them with such minimum supervision and tell them that actually these cases are related? And so we go back to the Hux Process Model. So it's not a coincidence because the Hux Process, in fact, is a popular model for studying crime data in the literature, and in particular in applied math in UCLA group. They have been using Hux Process there. But the one thing that hasn't been considered in the past is, a lot of times, they just consider the crime data using their times and location, but not the description, because description is a challenging case. It's a free text written by the police. And you have to consider all the problems in NLP, natural language processing, you have to face. Right? You have to filter out the non-informative words. That can be done by word frequency, word document frequency. Okay, that can be done, but it's written by, the officers have different style, and they can have typos, and sometimes, and then they joke about them themselves and saying, you write this in haste, and a lot of times it's nonsense. So how do we deal with that? You can't just translate this. You can't just, do sophisticated natural language processing, but we want to be able to capture the similarities in these descriptions. So what we end up doing is, so we still consider the Hux process, which captures this broken Indo effect, but introducing an additional term in our influence kernel. This additional term is an inner product of this H, which is embedding. So embedding is is a technique in natural language processing, but we here in particular are using its embeddings as a marks for the Hux process. So this inner product captures the similarities between a potential future case with the nature of the case crime. Okay, so the inner product basically captures the similarity, and it's called the cosine distance, commonly used in natural language processing. So basically this means that if there's a similar nature, the crime captured by embedding HK is a vector, and then this is going to cause the future nature of the crime H more likely to happen. Okay, so by the way, this is appeared in this paper, Analysis of Applied Statistics. So how do we perform embedding? So we use the Gaussian-Bernoulli discrete Boltzmann machine. So you can view this as like one layer neural network, but it's essentially going to create a Gibbs distribution. And so on top of that, we also want to be able to select the keywords, because not all keywords are important. You can see some of them are important in defining MO, right? Different definitions of MO. And so we introduce a regularizer in the fitting of the Gaussian-Bernoulli discrete Boltzmann machine. This regularizer is a probabilistic regularization. So we want to make sure that the selected keywords is sparse in the probabilistic sense. But somehow, I think this optimization problem, it looks sophisticated, but actually how to solve this, and there are existing techniques. And this one is differentiable, so we can utilize some of the machine learning techniques, such as contrast gradient, sampling, and so on, to be able to solve this efficiently. And so some of the results, but basically these are the selected keywords. You can see it seems to make a lot of sense in the end, like marijuana, home, stolen, vehicle, windows, suspects, and so on. And this is the estimated of IJs, if you remember that model. In this case, we discretize locations. So this of IJ, and for example, look at here, each node represents one geographic location. And so the edge between them means that one has an influence to the other nodes. And by looking at this, you can sort of say, oh, there are some locations and having a strong influence to other neighborhoods. So if you want to have a tactic, patrolling of the police, then allocate the resource to these nodes will cause a bigger impact overall, and so on. And so, by the way, I just mentioned that why do we choose embedding is because the resulted log likelihood from here is also integrable, so it's computationally tractable. And so, quickly mention this has been implemented by Atlanta Police in 2018, and that was the first project we did with Atlanta Police. And this is the, we create this user interface for them. It's like a search engine that you can input and say, I'm interested in finding a particular incident, and can you return the top 50 most related cases by the analysis? And it's going to be projected on the map. You search, and then you can click on it. You can perform the investigation, and so on. And yeah, after that, we also did the Atlanta Police Zone Design. That's a different project that actually, as mentioned by Professor Jim Dai, is a finalist of Wagner Prize this year. Totally different, but not going to talk too much about it. I would be happy to chat if you're interested. So that's basically the second one. Okay, the third one is coming back again, tackle this problem of general influence estimation. How do we bridge the gap and fundamentally, hopefully, address the influence estimation problem together with the mu? And as we said before, if I focus on estimation of the alpha and the mu, but treating the phi, the influence over time, as being given, then especially when this phi is exponential, then we have a pretty tractable problem. However, this may not be desirable because exponential decay assumes that when an event just happened, it has the largest influence, and then it decays. This may not be the case if there's a delay. For example, in the neuronal network problem, then the influence may have a delay. It doesn't happen immediately. In COVID-19, one place become a hotspot, and may take some time for this influence to propagate. So we ideally want to have more general influence function, or maybe affluence influence function over time itself. So that is the purpose here. But as we mentioned, if I want to join estimate alpha and the phi, and then the problem is non-convex, and the likelihood involves this integral, which may not be integrable, which is difficult. And so what we tried is alternatively consider the following. So this come up actually from a elevator discussion with my colleague Arkady Nemrotsky. So you really have this encounter in the elevator, and they ask what you work on. He asked me what you work on recently. I said, okay, let's chat about a police story, and he got interested. And Anatoly Juditsky was visiting, so we point out this idea, and together with my student, this whole project. So now suppose that we can discrete-time the time and location. So this is a discrete-time version of it. And now I have a memory depth D. And if your discretization is fine enough, then if the event doesn't happen very often, you can have binary states. So you say at any given time t and location k, you either have an event or you don't. Okay? And now what the model we have? The model is to say, given the past, as periods ago, at some location L, how this will impact future event at time t and location k. And so one possibility, since it's just binary, we can capture this through a logistic model. And so you say that the influence is captured, so mimicking very similar to the Hux. You say I have a baseline intensity, and I also have this influence kernel, which captures the event at node L to node K as periods ago. Okay, and those are the data. And so now what we have is, let's try to estimate its parameters, beta k, and this is like the tensor, the influence tensor we're trying to estimate. It has 3 arguments. Okay, and so, and then also we have a sigma outside here. And for logistic regression, it's a sigmoid, but you can also choose it to be other activation function, ReLU, hypertonic balance. And it turns out that this model is pretty much the same as a one-layer neural network in feed-forward RNN or convolutional neural networks. Okay, and so, which is great, which means that we can handle very large problems using what they have done, developed for RNN and CNN, to estimate these betas. So the betas in this context is known as the local filters. And so, okay, getting back to here, right, we can, and what's more interesting is even that we can say something, not just solve this problem, but also have performance guarantees. If it's just one layer neural network, means that if it's just one activation function. So 2 minutes covering what's the idea is the conditional intensity function can be written as a link function applied on a linear combination of the data. This beta is a long vector, contains all the parameters. And so if I just solve the least square problem, which is like fitting a one-layer convolutional neural networks, the problem is non-convex. It's known to be non-convex. And however, I guess there's some recent developments for Arkady and Juditsky and saying let's consider instead of least square, but you can construct a variational inequality with monotone vector field, and this corresponding problem can be convex. Okay, so instead of solving least square, but looking at this VI induced by a monotone operator. This monotone operator looks like this. It is not a gradient vector, but it's almost like a gradient vector. It doesn't need to be corresponding to a gradient vector of a convex problem, but solving this, and this can be solved efficiently using, for example, gradient descent, projected gradient descent, or any of the favorite methods, first order methods, and then it's a convex problem. And so skip this slide. And also this is going to be, since it's convex, we can actually have performance guarantee. This is a little bit counterintuitive because usually yourself fitting a one-layer neural network, you'd say the problem is non-convex. But if we solve it alternative using VI with monotone operator, the problem becomes convex, and we can have the performance guarantee. And in terms of recovering the beta, underlying beta parameters, and this upper bound actually is also instance-based. So depending on the data we have, we can establish this upper bound. So that's pretty useful. It roughly tells you whether or not you have a good estimate. Some simulation to show that actually this indeed recovers the underlying parameters. And as you can see, in this case, we artificially introduced these nonlinear, non-monotone influence function, but they can all be covered pretty nicely. And you can introduce other structures, such as I want this influence kernel to be low rank. It's a low rank tensor, so this can be incorporated into the problem as a regularizer and still be analyzed. So we have follow-up work on this. I guess we're almost running out of time, maybe 1 minute, so maybe in maybe a minute I just want to say this can be extended. We talk about like binary observation either exists or not, but actually I can extend this to categorical information. So in machine learning language, it just means instead of looking at logistic regression, let's look at multi-class, right? So you can have a softmax instead of sigmoid. That similar story holds. And I tried this on the real data since we talk about Atlanta police and tried two different kinds of categories. And this is one of the results. Basically, you look at the downtown Atlanta, divide the region into 4 by 4, so 16 locations. And this is the influence. Okay, this time it's general influence that captures influence between location and how this varies over time, and how different kind of crimes influence each other. Burglary and robbery, sometimes they're related. And you can see, for example, here, the influence is gradually time varying, and it doesn't occur at the first moment. There is a delayed effect. And we're talking about this as a natural framework for prediction. So we tried this simple validation whether or not this is a meaningful prediction. So we take our model and see whether or not this can be used to predict the chance of getting robbed at one location. So you can see here 2 versions of the prediction, but I think the numbers make sense. And keep in mind, this is the chance of getting robbed is not very high, fortunately. So it's a small probability. And so, for example, here, the true probability of robbery is 0.0017, and with this, you can predict this to be 0.203. And at this particular location, the chance of having a burglary is 0.0483, and the prediction is this. So the numbers are, this one seems to be matching, capturing certain nature. I wouldn't say, we're doing everything because it's a fairly simple model, but yeah, and we also use this for other applications such as solar power, anomaly prediction, collaboration with Argonne, and for Poisson observations. I think we're running out of time, but just want to mention that recently we also extend this to more general representation of the kernels using neural networks. This is not a simple neural networks, but some guarantees, and then all kinds of neural networks. I would happy to chat more if there's more time, but also use this to capture COVID-19 spread pattern and maybe show you like one thing you can see. The result is highly interpretable because we couple neural network with statistical models. So you can capture how the influence varies over space and time. And so the training doesn't need to be done by maximum likelihood. They also extend it to other, for example, using imitation learning, MMD type of metric, ADV0 type of training. So you can do this for one class of data, not necessarily MLE. It's not tailored to that. All right. So with this, I would like to thank all my collaborators, and if you're interested, I would be definitely happy to chat more. I think I'm really enjoying working in this area because it's the interplay between statistics, probability, and optimization, and finds many interesting applications. All right, so that's it. Thank you, everyone, for your attention.
Maybe any question?
Yes.
In the last topic, where you said sort of conditional on the influence function alpha and whatever the other guy was, mu, I think, were a convex problem to identify those. Where I thought you were going to go was conditional on the alpha and the phi. Choosing the shape of the influence function within some class would be a convex problem. Is that true, or is that not a productive way to go?
Yeah, that's another way to go. I think that's exactly the right observation. So the fundamental problem is you want to capture some phi, right? So you have the phi function which depend on t and ti, right? This is the fundamentally, or you can say this is this. So you have a kernel, for example, this phi tau. So how do I represent this phi? You can write this, if you have a set of good basis function, you can represent this using, say, alpha, let me use a different parameter. So maybe gamma, I, and just have some basis function like this. For example, if this is a overcomplete basis, or if they're orthogonal, estimate its coefficients, that can be done as well. Okay. Yeah, so that problem is going to be convex as well. So I basically took another route and talk about a discrete version of it and drawing connection to CNN, basically just saying that it's computationally efficient.
Great.
Yeah.
It's great to confirm that, thank you.
Sure.
I guess what I'm wondering is,
Mhm.
why did you take the other approach? Is it better?
Why do I take the discrete timing
Yeah.
approach?
Yeah.
Well, here you need to choose the basis function. Okay. And so what is a good choice of the basis function is not clear. And in fact, I didn't cover the last part of the talk, which is, in fact, one way of treating this is you can parameterize this by neural networks. So I can use neural networks as some kind of a basis function, and then I can treat my neural networks to achieve the goal. But of course, if your favorite choice is a wavelet or some kind of spline function, and that can be used here as well. So that has been done actually, not by us, but by other people in ICML. Yeah, but the estimation procedure and so on sort of depend on the choice of the B. Yeah.
Okay, so I hope there's a clarification. Katia, you had a question?
Well, yeah.
Maybe
now
hopefully
I-
not an answer, okay.
Now I started thinking about this question.
Yeah.
But yeah, I'll ask my original one, just it's a very basic question. So, you were showing that you predict the probability of, say, burglary, right?
Mhm.
Or robbery, which are low, and it's not very clear, like, how, it's hard to make an accurate prediction of that, but you really probably want to predict in these applications, right?
Mhm.
What is the most likely area that will be rolled next?
Mm-hmm. Yes.
Because in
yes.
some sense, right? It's like
That
really
is-
qualitative prediction.
Right,
Would
right.
it make that problem in some sense easier?
That's a
Yeah.
great question, actually. So, in fact, we tried this approach in a recent paper, which is predicting hotspot for COVID-19.
Right.
So based on this probabilistic model, I want to predict what is the most likely place
Exactly.
to be a hotspot. So I can evaluate the probability of a place become a hotspot, and I can rank these locations and say these are the top 10 locations that are likely to be hotspot. That paper is on my website, if I can talk to you all offline. And so I think indeed that is a more meaningful problem, and the burglary is more like a, sanity check thing and making sure that this actually matches the reality sort of sense.
All right, in the interest of time, we stop here, and Yao will be here tomorrow as well, and so you can catch with her to talk more. Okay, let's thank her again.